Following up on our particles presentation, now we're going to follow up with how atomic number and atomic mass are calculated. Atomic number and atomic mass are based off the number of protons, neutrons, and electrons. And up here, I have the first 8 elements off the periodic table and set up for us to kind of follow along. Up here, we start out with hydrogen. Hydrogen's atomic number is 1. By its atomic number being 1, that means that it has 1 proton. And since every neutral atom has the same number of electrons, you'll notice here 1 proton, 1 electron. Our next atom and all the atoms today have the same number of protons and electrons since the charge is equal for the positives and negatives. Where we have a variance in each atom and where the atomic mass comes from is really the number of neutrons that are involved. So you'll notice hydrogen, generally speaking, has an atomic mass of 1. Well, if one of those items is a proton, then that means there are no neutrons in an atom of hydrogen. Now, there are some in different isotopes, but most generally, most isotopes of hydrogen have no neutrons. As we move down the list, though, we get to helium, and helium has 2 protons, but the atomic weight of helium is generally 4. Well, those 2 missing pieces are generally 2 neutrons. As we go down, boron has 3. The weight is 6.9. Most of the time it has 4 neutrons in it. So the difference between the atomic mass and the atomic number is the number of neutrons. Now, as you'll notice here with the atomic weight, it's big numbers with decimals and stuff. That's because we have isotopes. Basically what that means is that not every atom of one element weighs the exact same. For example, there is hydrogen 1, hydrogen 2, and hydrogen 3, and many people commonly know those as protium 1, deuterium 2, and tritium 3. Each one of those has a different mass, 1, 2, or 3, because they have neutrons. Well, there's not much tritium and there's not much deuterium, so the average of all 3 hydrogen atoms on the planet is only 1.008, causing the average to be just slightly above 1. So in a few isolated instances, there are more. Now, on the periodic table, there are different instances where we do have many more neutrons and isotopes they have to contend with, but hydrogen is not one of those examples.